In this chapter, we are going to see about diffraction. In this chapter, we are going to discuss about definition of diffraction, Fresnel and Fraunhofer diffraction. In Fraunhofer diffraction, we are going to see about an interesting topic, which is diffraction of a single slit. Definition of a diffraction. Diffraction is a bending of waves around the sharp edges into the geometrically shadowed region. This is an example of a diffraction. Here you can see that the bending of region into a geometrically shadowed portion. This is called as diffraction. An example picture of diffraction. Next we are going to see about difference between Fresnel diffraction and Fraunhofer diffraction. In Fresnel diffraction, spherical or cylindrical wavefronts undergoes diffraction. In Fraunhofer diffraction, plane wavefronts undergo diffraction. In Fresnel diffraction, light wave is from a source at a finite distance. It means the source and the screen are kept at finite distance. In Fraunhofer diffraction, the light wave is from source at infinity. It means the screen and the source are kept at infinite distance. In Fresnel diffractions, for an laboratory conditions, convex lens need not to be used. It means the lens are not to be used. In Fraunhofer diffraction, the laboratory conditions, the convex lens are to be used. It means the convex lens are must to be used. In Fresnel diffraction, it is difficult to observe and analyze. In Fraunhofer diffraction, it is easy to observe and analyze. These are the difference between the Fresnel and the Fraunhofer diffraction. Now we are going to see the diagrammatic form of Fresnel diffraction and Fraunhofer diffraction. In the Fresnel diffraction, now we are seeing that the source and the screen are kept at finite distance. In Fraunhofer diffraction, the screen and the source are kept at infinite distance. In Fresnel diffractions, you are seeing that the lens are not used. In Fraunhofer diffractions, you are seeing that the convex lens which are passing in a diverging manner are used. These are the diagrammatic forms of Fresnel and Fraunhofer diffraction. Next, we are going to see about an interesting topic, which is diffraction of light at a single slit. Screen, slit, lens, source, which is an S, and monochromatic light, which is a single wave light, have a wavelength lambda. This is an Fraunhofer diffraction setup. The distance between the screen and the source is effectively infinite. The L1 is a convex lens where the light comes out in a diverging manner through the lens comes in a parallel. The parallel rays perpendicular, then it is called as a wavefront, where here it is an plane wavefront where it is W and W dash. Now we incident the narrow slit in a width A, a rectangular slit with A, and B, which considered as an width A. When a wavefront passes through a narrow slit, it dashes and forms a diode. These points are called as fresh source disturbance. It emits the secondary wavelets and produces. It gets diffracted at a various directions. Now you are seeing the fresh source of disturbance are producing the secondary wavelets in a various diffraction manner, which are hitting in various directions. Now we are going to take the particular points which are getting focus point and focus plane. This is a lens, convex lens L2. Physically, the source and the incident is near, but it is effectively so far. After the incident, it produced the fresh source waves and produced the secondary wavefronts and touches the point P focal plane at a focus P. C is an central maxima. Interference may form the bright and the dark band. Now you are seeing that the diffraction of a light at a single slit forms the central maximas, secondary minimas, secondary maximas. The secondary minimas and secondary maximas are subsidiary minimas and maximas. The path difference of AB is equal to Bn, where now we are going to find out the wavelength of Bn is equal to A sin theta, whereas the central maxima, which considered a rays moving parallel to the ray of incident, the path difference is 0 and passes and reaches the C. It is called as central maxima or constructive interference, whereas Bn is equal to A sin theta. In central maxima, the path difference is equal to 0. This is called as diffraction of an light at a single slit. Next, we are going to see about secondary minimas. First, secondary minimas. I am considering a slit, a fresh source of disturbance A, B. I am dividing the slit into two equal parts, whereas A sin theta 1 is equal to lambda. Bn, I am dividing the slit into lambda by 2 and lambda by 2 portions, where theta 1 is equal to angle of diffraction and A is equal to width of a slit. Second, secondary minimas. I am considering a slit again, fresh source of disturbance A, B, dividing the slit into 4 equal parts, whereas A sin theta 2 is equal to 2 lambda. Bn, whereas lambda by 2, lambda, 3 lambda by 2 and 2 lambda, whereas A sin theta 2 is equal to 2 lambda. For nth minima, A sin theta n is equal to n lambda, where n is equal to 1, 2, 3 and so on. N lambda by A is equal to sin theta 1. So now we got the equation of secondary minimas. Next we are going to see about secondary maximas. In that, first secondary maximas. I am saying considering a slit with a fresh source of disturbance A and B. Now I am dividing the slit into 3 equal parts, whereas Bn is equal to, for differentiating the minimas and maximas, A sin dash theta 1 is equal to 3 lambda by 2 and dividing the slit into AC, which is equal to lambda by 2, CD lambda, DB 3 lambda by 2. Next, second secondary maximas. Same, I am considering a slit, fresh source of disturbance A, B, and now I am dividing the slit into 5 equal parts. Lambda by 2, lambda, 3 lambda by 2, 2 lambda and 5 lambda by 2. This is Bn is equal to A sin dash theta 2 is equal to 5 lambda by 2. For nth maxima, A sin dash theta n is equal to 2n plus 1 lambda by 2, whereas n is equal to 1, 2, 3 and goes on. 2n plus 1 lambda by 2a is equal to sin dash theta n. So now we got the equation of secondary maximas. Next, these are the setup of diffraction of a light at a single slit. This is the whole setup. Now we are seeing that the intensity distribution curve of central maximas, secondary maximas and minimas. Here you are seeing that central maxima. As usual, I said before, the central maxima, the path difference is equal to 0, so then it gives a bright band. This is the secondary minimas, which gives us dark band, where the intensity decreases. Next, we are seeing that secondary maximas, where it gives a bright band. This is the diffraction of a light at a single slit, which gives alternatively bright and dark band. This diffraction of light at a single slit, which gives alternatively bright and dark band. Next, we are going to see about intensity of a distribution curve, where the intensity is larger, then the path difference is equal to 0 and it gives the central maximas. Then the lambda by 2, 2 lambda by d, 3 lambda by d, it gives an subsidiary secondary minimas and maximas, whereas the light decreases and give the dark and the bright band. This is called as intensity of the distribution curve. Now in this diagram, we are seeing that A which is a width, a rectangular slit, D is a diameter. Now we are going to find out the wavelength. Angular width of central maxima 2 theta is equal to 2 lambda by A, whereas lambda is an wavelength, A is a rectangular slit width, which is called as A. Theta is equal to lambda by A is equal to AC by D. Before I am cancelling the both sides 2. Linear width of central maxima is equal to 2 lambda D by A. I am multiplying the diameter to it. Angular width of secondary maximas is equal to n plus 1th minus nth. N plus 1th lambda by A minus n lambda by A. Whereas I am getting minusing it and getting the linear width of secondary maxima is equal to lambda by A. For angular width of secondary maxima, I am considering it as a notification of a beta, which is equal to lambda D by A. Just I am multiplying the D into it. For central maxima, for an angular width of an central maxima, beta naught is equal to 2 lambda D by A. Just I am multiplying the diameter to it.